Hello, welcome to the Physics with Keith GCSE Summer School, and this week's questions come under the title Nuclear. And here they are. So I'm going to do what I do every week and give you some clues and some hints of how to answer them, and then on Saturday we can go through some of the answers and maybe address any questions or problems you have. Question 51.2 is all about Nuclide notation. And that is the notation where, as you can see here, we can identify the number of protons, electrons and neutrons in a neutral atom of a particular isotope. So in the example I'm giving here, this is carbon. We know it's carbon because it has the chemical symbol C. And then we've got two numbers, 6 and 14. The number on the bottom is called the atomic number, or sometimes called proton number. And this is the number of protons. And the number on the top is sometimes called atomic mass, sometimes called nucleon number. And this is the total number of nucleons. A nucleon is either a proton or a neutron. And so the total number of neutrons in this particular carbon isotope is 14 minus 6, which is 8. Quick bit of revision for anyone that's forgotten. Within the nucleus of an atom, there are protons, which are positively charged. There are neutrons, which are neutrally charged. And around the outside of the atom, if it is a neutral atom, there are electrons. I keep saying if it's a neutral atom, of course, if it's not neutral, it's not an atom. Atoms are neutral by definition. Well, that is a terrible diagram. And there we go. So how many electrons are in this neutral atom of carbon-14? Well, there are 6, because there are 6 protons, and in a neutral atom there are the same number of protons, 1, 2, 3, as there are electrons, 1, 2, 3. 52.8 asks you about alpha decay, and I'll give you an example of alpha decay. The most common naturally occurring isotope of uranium, uranium-238, is represented with this nuclide here. Quick check, how many neutrons does it have? 238 minus 92, that's 146 neutrons. Anyway, this uranium atom, let's say it decays via alpha decay. You might want a periodic table for this next part, and you can Google to find one of those. When uranium decays via alpha decay, let's see if I get in the middle of the screen. There we are. When uranium decays, it turns into thorium. Well, how does that work? How does one element change to another? Well, alpha decay means we emit a particle called an alpha particle. An alpha particle consists of 2 protons and 2 neutrons. That means an alpha particle has an atomic number of 2. What's the atomic mass? That's going to be 4 because it's 2 protons and 2 neutrons. So the last stage of this is making the numbers balance. 92, let's go along the bottom, 92 is how many add 2? Well, that's going to be 90. I can do that. And along the top, 238 is how many add 4? Well, I can do that as well. That's 234. And so thorium from this particular decay of uranium has 234 nucleons. That's 144 neutrons. And you'll be given a question similar but different to this. Now, the complicated bit with this question is how you enter your answer. So the question you'll actually be given is about plutonium-239 and filling in the numbers. And the way you would do that is you would click the little number tab here, and I've told you already that alpha has 2 protons, so you would pick up the 2 and drag it and pin it to the bottom left of that diagram. And I've already told you that there are 4 nucleons in alpha, so you would pin it there. And you can check on the bottom that it looks like you think it will look like. Well, let's just do something totally balmy to see if hello, that didn't work. Let's do something totally balmy to see whether I can break this. Yes, here we go. I'm managing to break it. So if you want to enter a number, perhaps more than one number, Down here, you think uranium 92. I know that. So I take this thing here, I drop it here, I take the 2 and I try to drop it there. I end up with 9 squared. It's all looking a little bit wrong. So if I want a number that's more than a single digit, what I do is I click and click. I don't drag, I click and click. And there we are, I've got 92 now, so I can drag that there. And if I wanted a different number, let's do something wrong. There we go, 654. Well, let's just see if that's right, shall we? No, it's wrong. Okay, so you'll put what you think is the correct answer there. 52.4 is going to ask you about beta decay. This is a different type of radioactive decay. And in this one, rather than having the emission of an alpha particle, as you get in alpha decay, you get the emission of a beta particle. The clue's in the name. So what is a beta particle? It's that. Now this may look a bit confusing to you. How can you have -1 protons? Yes, the notation's broken down a little bit. What that means is it's an electron. This is an electron that's emitted from the nucleus of an atom. And so you would have to then decide what the numbers are here and what the numbers are here, doing exactly the same thing you did last time. So Z, well, that's going to be Z plus 1 minus 1. So I can fill that in. And, well, A doesn't change. Check your numbers, fill in the blanks, and get the answer right. Now 53.1 talks about the timing of these sorts of decays. Alpha decay and beta decay that emit alpha and beta radiation. You never know exactly when an atom that is radioactive is going to decay. You just can't predict it. But you can do some statistics, and it turns out that there's a probability of decay. Now, I'm not going to go into the details because that's A-level physics, but I will tell you that if you get enough atoms together, then in one half-life, that's a period of time we call a half-life, half of those radioactive nuclei have decayed. And from what's left, another half-life's time, which is the same amount of time, one half-life, half of what's left has decayed. And in one half-life after that, half of what's left has decayed, and so on and so on. So if a half-life was a day, and I started with 100 of this radioactive isotope, then one day later I would have 50, and another day later I would have 25. And so on and so on. Each day I halve the amount. You'll notice I haven't got any decimals here. These are all round numbers. That's because I can't have half an atom. Well, obviously I don't have a half-life of a day in the question that we're talking about. We're talking about carbon-14, which we're saying has a half-life of 5,700 years. But it's the same idea. Every 5,700 years, we halve the amount we've got. So if I start here and I say 5,700 years ago, how many did I have? I had twice as many. And in 5,700 years' time, how many will I have? Half as many. And that's how half-life works. Now, there's another definition of half-life that's not to do with the amount of or the number of nuclei, but it's to do with the activity. It's a little bit more complicated, but actually the maths is exactly the same. Basically, the more of a radioactive isotope I've got, the more atoms I have, the more of them will decay, and therefore the more alpha or beta particles will come out of them. The number of particles that come out per second we call the activity. And so as the number that is left keeps halving, the number of particles that are left keeps halving, so does the activity. That keeps halving as well. And so if instead of number of nuclei being 25, we said that we detected 25 alpha particle, let's do beta, 25 beta particles per second coming out of this source, then 5,700 years ago we had twice as many coming out per second, and in 5,700 years' time we'll have half as many coming out per second. And activity is measured in a unit called becquerels, which has the symbol capital B, lowercase q. Gotta be a capital B and a lowercase q. Small b, small q is wrong. Big B, big Q is wrong. Now 53.3 is the same sort of question, but it doesn't just go one half-life either side, it bounces a few half-lives. So be prepared to do some arithmetic, not on your fingers, perhaps use a calculator, but write down your numbers as you go along so you don't make a mistake. 54.2 is about fission, but don't let that scare you. Fission is where one nucleus can split into two daughter nuclei, two smaller nuclei. So a uranium atom can split into two daughters. In the example here, in 54.2, the uranium splits into krypton and barium, but it doesn't have to. It can split into different elements as well. It's a certain amount of probability in it. And in this question, what you need to do is the same approach you've taken in 52.8 and 52.4. That is, you add up the numbers along the top, you add up the numbers along the bottom. And what you'll find is there are some neutrons missing, unaccounted for. You work out how many neutrons are also emitted in this fission reaction, this splitting of a heavy nucleus, and that's your answer. And the last question, 56.2, is about the energy released in nuclear reactions. Now, this question's going to have you dealing with some very small numbers. So you have to make sure you can use standard form, and you'll be using this equation here. Now this equation is the most famous equation in all of physics, E equals mc squared. And it tells you that there is an equivalency between energy and mass. In fact, energy can be converted into mass, and mass can be converted into energy. And that's where the energy from these nuclear reactions comes from the conversion of mass. If energy is released in the reaction, mass is destroyed. And if you've been told mass cannot be created or destroyed, you've been told wrong. Energy that's released in a reaction is created. So if you were told energy cannot be created or destroyed, you were told wrong. But energy divided by mass, that's constant. And that constant is called the speed of light squared. The speed of light itself is a very big number indeed. 3 times 10 to the 8 meters per second. When you square that, it's 9 times 10 to the 16 meters squared per second squared. That is a huge number. So where does this help us? In the question, you'll be looking at the mass of the things that go into a nuclear reaction, the mass of the things that come out, and comparing the two. And what you'll find is the mass afterwards in total is less than the mass before. You'll then use this equation to find out how much energy that is equivalent to. In other words, how much energy is being released. And the question goes on to ask you a little bit about power, so you'll have to remember back to the energy section, which I quite like. And there's some rather nice questions that involve quite a lot of challenge. You'll have to really read the question and try to understand what's going on. But that's why it's the final question on here. It is the most challenging, and it's the one I expect we're going to be going through on Saturday.